In this module, you will learn about the intermolecular forces. The attractive intermolecular forces are often called van der Waals forces in the honor of Dutch physicist Johannes van der Waals. Van der Waals forces can be classified into dispersion or London forces, dipole-dipole forces, and dipole-induced dipole forces. Let's study each of them in detail, starting with the dispersion forces. The existence of dispersion forces was first suggested by Fritz London, and hence these forces are also known as London forces. We know that atoms and non-polar molecules have no dipole moment because their electron cloud is symmetrically distributed. However, due to the constant motion of the electrons, an atom or molecule can develop an instantaneous or transient dipole when its electron cloud is distributed asymmetrically about its nucleus. Let's understand this through an example. Suppose we have two atoms labeled as A and B in close vicinity. For a moment, let's assume that the electron cloud distribution in atom A becomes unsymmetrical. That is, the electron cloud is more on one side than the other. Due to the unsymmetrical distribution of the electron cloud, an instantaneous dipole is developed on the atom A. This instantaneous or transient dipole distorts the electron cloud on the other atom. That is, atom B, which is close to it. As a result of this, a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. This force of attraction between the two temporary dipoles is known as dispersion force or London force. This force is important only at a short distance, which is limited to 500 picometers and is inversely proportional to the sixth power of the distance between the two molecules. Another type of intermolecular force is dipole-dipole forces. The dipole-dipole forces are attractive forces that act between the polar molecules with permanent dipole. The ends of the dipoles in a polar molecule possesses partial charges which are represented by the Greek letter delta. For example, in hydrogen chloride, due to the greater electronegativity of chlorine, it attracts the electron cloud more towards itself, and thus its end has a partial negative charge and the hydrogen end has a partial positive charge. The attraction between the positive end of one polar molecule and the negative end of the other polar molecule forms the dipole-dipole forces. The more polar the molecule, the greater is the strength of its dipole-dipole interaction. Due to this, the boiling point of polar covalent compounds is relatively higher than that of non-polar covalent compounds. Dipole-dipole forces are stronger compared to the other London forces. But due to the involvement of only partial charges, they are weaker than the ion-ion interactions. The dipole-dipole interaction energy between the polar molecules is inversely proportional to the sixth power of the distance between the two polar molecules. Polar molecules can interact both by dipole-dipole forces and also by London forces of attraction. The third type of forces are dipole-induced dipole forces. These attractive forces operate when a polar molecule with permanent dipole induces a dipole in a non-polar atom or molecule by deforming its electron cloud. Consider the nonpolar chlorine molecule brought in the vicinity of a polar molecule, such as water. The permanent dipole of water molecule polarizes the electron cloud of chlorine and induces dipole on the electrically neutral chlorine molecule. Thus, dipole-induced dipole interactions come into existence between water and chlorine molecules. The induced dipole moment depends upon the dipole moment present in the permanent dipole and the polarizability of the nonpolar molecule. Larger the size of the nonpolar molecule, higher is the polarizability, and hence greater is the strength of the attractive interactions. In this case also, interaction energy is inversely proportional to the sixth part of the distance between the two interacting particles. A special case of dipole-dipole interaction called hydrogen bond exists in the molecules with highly polar NH, OH or HF bonds. This intermolecular force is stronger than the van der Waals forces of attraction, having interaction energy of the order of 10 to 100 kilojoules per mole. Therefore, hydrogen bond is a powerful force in determining the structure and properties of many compounds such as proteins and nucleic acids. Have you ever wondered why it is very difficult to compress the solids and liquids? Intermolecular forces can also be repulsive in nature. When two molecules are brought closer, the repulsions between the electron clouds and between the two nuclei of the molecules come into play. The magnitude of repulsion increases rapidly with a decrease in the distance between the molecules. In solids and liquids, the molecules are already close to each other, and hence, when we try to compress them, the repulsive interactions would further increase. Hence, they resist compression. The physical state of a substance not only depends on the strength of intermolecular forces that exist between its atoms or molecules, but also on the thermal energy of atoms or molecules. The energy of a body arising from the translational, rotational, or vibrational motion of its atoms or molecules is called the thermal energy. It is the measure of the average kinetic energy of the constituents of the matter and is directly proportional to temperature of the substance. The intermolecular forces of attraction between the molecules try to bring the molecules closer. On the other hand, the thermal energy possessed by the molecules, which results in the movement of molecules, tries to keep them apart. The balance between the intermolecular forces and the thermal energy of the molecules is responsible for the physical state of matter. In gases, the intermolecular forces of attraction are the weakest, while thermal energy is the highest. While the compression brings the molecules to close vicinity, the lowering of the temperature brings about the liquefaction of the gases by decreasing the thermal energy of the molecules. You have now reached the end of this module. In this module, you learned that intermolecular forces are attractive and repulsive forces between the interacting atoms and molecules. The force of attraction between the two temporary dipoles is known as dispersion force or London force. Dipole-dipole forces are attractive forces that act between the polar molecules with permanent dipole. The dipole-dipole forces are stronger compared to the other London forces. Dipole-induced dipole attractive forces operate when a polar molecule with permanent dipole induces a dipole in a non-polar atom or molecule by deforming its electron cloud. A special case of dipole-dipole interaction called hydrogen bond exists in the molecules with highly polar nitrogen-hydrogen, oxygen-hydrogen, or hydrogen-fluorine bonds. The energy of a body arising from the translational, rotational, and vibrational motion of its atoms or molecules is called the thermal energy. The balance between the intermolecular forces and the thermal energy of the molecules is responsible for the physical state of matter. The physical state of matter depends on the strength of intermolecular bonds and the thermal energy of the particles involved.